the previous lecture we introduced the basic economic order quantity model whose stock versus time relationship is shown in this figure. So, Q is the economic order quantity or the quantity that we order every time we place an order. So, the model works as follows. Let us assume that we have just received Q units that has been ordered earlier. We also assume instantaneous replenishment, which means as soon as the order is placed the items arrive, and then we consume this item at the rate of D till it reaches the stock position reaches 0, and then we place another order and instantly get this Q, and this process goes on forever. We also derived an expression for Q, and we derived that Q is equal to root over 2D C naught by Cc, where D is the annual demand, C naught is the order cost or cost of placing an order, and Cc is the cost of holding or carrying inventory. This formula was derived when we tried to minimize this expression. Total cost is equal to D by Q into C naught plus Q by 2 into Cc. Now, this total cost is the total annual cost of inventory, and in this model the two relevant costs are the ordering cost and the inventory carrying cost. We do not consider shortage cost because one of the assumptions is no shortage or back order is allowed, which means that the stock position will come right up to 0, it will not go beyond that. So, it will come up only up to 0, so no shortage cost is allowed. We may or may not include the actual cost of the item. We saw in the previous lecture that the actual cost of the item is D into C per year, this is per year or per given time period. So, it will be D into C if it is per year, and it does not depend on Q, the ordering quantity. Therefore, when we differentiate this, the term D into C does not contribute anything, and it is customary therefore to leave out that term, the term that involves the actual cost of the item, and consider only the ordering cost and carrying cost, and then optimize it to get this. Now, let us work out a numerical example to understand a few more things about this formula and the use of this formula. Now, let us take an example where D, which is the annual demand of the item, is say 10,000 per year, C naught, which is the ordering cost, is say rupees 300 per order, C, which is the unit price of the item, let us say is rupees 20 per unit, and I is the interest rate, which let us say is 20%. So, Cc will now be defined as I into C will be 20% of rupees 20, which is rupees 4 per unit per year. Now, when we apply this formula, we are now given D, C naught and Cc 10,000, 300 and 4. So, we apply this formula to get Q is equal to root over 2 into 10,000 into 300 by 4, which on simplification would give us 1224.74 units. We have already seen that this Q, when we derived it, Q was root over 2D C naught by Cc. We take only the positive quantity, we do not take the negative quantity because Q represents an order quantity. So, you get 1224.74 units as the economic order quantity in this case. Now, this means that whenever we order we will order for 1224.74 units to begin with. Of course, we will have questions like how can I order for a fraction of a unit and so on. We will answer those questions as we move along, but right now based on this formula we say that every time we place an order, we order for 1224.74 units. Now let us also try and find out the cost associated with this. So we need to substitute Q equal to 1224.74 into this in addition to D, C0 and Cc to get this total cost. Now instead of substituting 1224.74, let us try and substitute this value, which is the value of the economic order quantity, this equation for Q, into this and compute this total cost as a function that does not directly use Q. Let us compute this in terms of D, C0 and Cc. So let us go back and substitute. Now total cost Tc is equal to D by Q into C0 plus Q by 2 into Cc. Now Q is given by root of 2D C0 by Cc. So on substitution we will get D C0 by root over 2D C0 Cc plus root over 2D C0 by 2 into Cc. So this on simplification would give us root over D C0 Cc divided by root 2 plus root over D C0 Q by 2 into Cc. I am sorry. So Q is root over 2D C0 Cc. Q is root over 2D C0 by Cc, Q by 2. So this 2 comes here, this Cc comes here. So on simplification, this root over Cc and this Cc will cancel to give another root over Cc. So root over D C0 Cc divided by root 2, because there is a root 2 here, there is a 2 here. So we get this expression. This on further simplification will give you 2 times root of D C0 Cc by root 2, which will give us root over 2D C0 Cc. So we can now write the total cost in terms of only the known parameters, which are D C0 and Cc, and not in terms of the computed number, which is Q. So the total cost at the optimum, the minimum total cost that we will incur, is root of 2 into D into C0 into Cc. And in our example, when we substitute, we will get root over 2 into 10,000 into 300 into 4, which on simplification will give us 4898.98 rupees per year. Now this quantity does not include the actual cost of the item. The actual cost of the item, if we take a 1 year period, will be 10,000 is the demand per year, say 20 is the unit price. So 200,000 will be the actual cost of the item. So we could, if we say that the total inventory cost is 4898.98, it means we are only giving the order cost plus carrying cost for the year, and we have not included the actual cost of the item. If we say 204898.98, it means we have also added the actual cost of the item per year. Now from this formula we also observe a very interesting thing, which is at the optimum, that is when we substitute root over 2D C0 by Cc, at the optimum the component of the order cost and the component of the carrying cost are equal. So when we do this optimization to find out the value of the economic order quantity, we are essentially trying to find out that value of Q for which the order cost is equal to carrying cost. Therefore, the total cost is 2 times the order cost and carrying cost, which comes to this expression. Now, let us also try and draw a graph that kind of depicts or shows the economic order quantity. So, if we look at now cost versus order quantity, cost versus order quantity. Now, the order cost is of the form d by q into C naught. D and C naught are known, q is the unknown, so it is constant divided by q. So, when we draw this, we will get the curve will be like this. This will be the order cost curve, it will be a rectangular hyperbola which will show this d by q into C naught. This is the order cost. Carrying cost is q by 2 into Cc, which is constant into q. So, it is a line which passes through the origin. So, the carrying cost will be like this. Now, we have already said that the economic order quantity is the point where the order cost is equal to the carrying cost, which we got from here, they are equal. So, this is the economic order quantity where the two curves intersect. This I call as q star, which is the economic order quantity. You can write q equal to, or you can write q star equal to, the best value of q is called q star. And this is the place where the total cost is also minimized, because we are substituting this, which is the minimum value, into the total cost function. So, we will have this is these two are equal. So, this is the point. So, the total cost curve will actually look like this. So, this is how the total cost curve will look like. Now, this is the Tc star, this is the root of 2d C naught into Cc. So, the total cost is 2 times this, and it happens for the corresponding q star. So, this is how the costs behave. This is Cc carrying cost, this is Tc equal to order cost plus carrying cost. Now, let us try and answer a few simple questions. Now, one is, when we did this calculation, we have now found out that the economic order quantity is 1224.74. So, the first question that we would ask is, are we justified in treating this q order quantity as a continuous variable? When we differentiated this and then we set it to 0, when we set the first derivative to 0 to find the minimum, we assume that q is continuous. Now, let us assume that we took q as a continuous variable. The assumption of q being a continuous variable was made considering the ease of the mathematical derivation for it. If q were to be defined as an integer variable, then the methodology to get it would be different. Since for convenience we define q as a continuous variable, we could easily set the first derivative to 0 and get the value and show that the second derivative is positive, indicating that this value is indeed a minimum for the plus value of q. Now, because of that, we also seem to get a number like 1224.74, which poses the question, how can I order a fractional quantity of the item? So, the simplest thing to do perhaps is to try and round it off to the nearest number, which could be 1225, let us say, and let us see what happens to the total cost, whether it is very different from the absolute minimum if we look at 1225. So, let us try and do some quick computations. So, when q is equal to 1225 TC is equal to. So now all we need to do is to substitute 1225 here. So TC will become 10,000 into 300 by 1225 plus 1225 divided by 2 into 4, which will become now when we substitute q equal to 1225, which is the upper integer value or the closest integer value to 1224.74, and substitute 1225 here as well as here, the total cost is, it remains at 4898.98, which is the absolute minimum. So between 1224.74 and 1225 there is absolutely no loss. So instead of implementing 1224.74, we could implement 1225 if we have to keep q as an integer. Then comes the next question. Now can my vendor supply 1225? Suppose my vendor is willing to supply only in multiples of 100, then I may have to consider 1200 or I may have to consider 1300, whichever is minimum. So let us try and evaluate the TC for q equal to 1200. Now TC will become 10,000 into 300 divided by 1200. So 300, 1200 is 4. So 10,000 by 4 is 2500 plus, here we have 1200 by 2 is 600, 600 into 4 is 2400 is equal to 4900. Now here I am specifically showing the order cost component and the carrying cost component. Now if q equal to 1300, TC is equal to 10,000 into 300 divided by 1300 becomes 4907.69. Let us just look at one more calculation or two more calculations. Let us say the vendor can give only at 2000 and the vendor is giving at 4000. Now if the vendor is giving in multiples of 1000, let us say, then we are looking at say three numbers, q equal to 1000, q equal to 2000, let us say q equal to 4000. Now at q equal to 1000, which means the vendor is giving in multiples of 1000, the 10,000 by 1000, which is 10, 10 into 300, which is 3000, plus 1000 divided by 2 is 500, 500 into 4 is 2000, Now if the vendor will give us only in 2000, then this is 10,000 divided by 2000, which is 5, 5 into 300 is 1500, 2000 divided by 2 is 1000, 1000 into 4 is 4000, which is 5500. Now, if the vendor would give us only 4000, then it becomes 4000, 10,000 into 300 divided by 4000. So, this is 2.5 into 300, which is 750, plus 4000 divided by 2 is 2000, 2000 into 4 is 8000, $750. Now, let us try and understand a few things that we have calculated here, and let us try and show some of these into this graph and try to understand a little bit from this graph. Now, the first thing we did was to round this off to the nearest numbers. We tried 1225 and we realized that it just is the same, the total cost is the same. So, if the supplier can give in multiples of 1 or any integer quantity, then ordering 1225 is indeed economical. So, first lesson is that we need not really worry about the fact that we have a fractional number or a decimal number coming here. It can be rounded off to the next highest integer and there is absolutely no change in the total cost. Then we start looking at multiples of 100. Then we looked at the two closest numbers which are 1200 and 1300, and we actually realized that for 1200 the total cost was 4900, which is hardly a rupee more than the earlier one and is absolutely negligible. The increase is absolutely negligible, not even of the order of 0.1%, it is much less than that. So, one can use 1200. Now, even if we round it off to the higher 100, which is 1300, which is an increase of about 75, we still realize that the total cost has just become 4907, which is somewhat like 8 rupees more than this. So, the increase is 8 rupees on 5000, which is 1.6 rupees on 1000 and 0.16 rupees on 100. So, it is a 0.16% increase. So, there is a 0.16% increase if there is a 75 by 1200 into 100, which is roughly about 6% increase in the order quantity, is giving us a 0.16% increase in the total cost, which also shows somewhere that the total cost curve is kind of flat near the optimum, which is what we have tried to show here. It is quite flat here at this zone. So, even if you kind of play around with Q roughly in this area, the TC does not increase very significantly. For example, even if we go to 1000 and 2000, which is the two nearest thousands, if you want to approximate this, you realize that for 1000 the total cost is 5000, which is about 100 rupees increase, but for 2000 it shows about 600 rupees increase, which is a little significant. You are now talking of the order of 10% here. Here you are still not talking of the order of 10%, you are still talking of the order of 2% here. And if you really increase it to 4000, this is where you are talking of a very large increase of nearly 70–80%. So, as long as this Q is somewhere near, as long as any ordering quantity Q is near Q star, up to say 10% on either side of Q star, you realize that it is very flat near the minimum, and therefore, the effect of increase in cost is not very high. Only when you move the ordering quantity Q significantly away from this, either this side or this side, you realize that the total cost is very high. For example, if this is 1224.74, say let us say 4000 is somewhere here, and therefore we saw that it went up, total cost went up. Now when it is 4000, you also realize the total cost went up, the order cost is small, the carrying cost is large. So you see that the order cost is small, the carrying cost is large. As you move to the right of Q star, the carrying cost is going to increase, the order cost is going to come down. For example, if you look at 1300, order cost is coming down, carrying cost is going up. 2000, order cost is coming down, carrying cost is going up. Less than that, 4000, order cost is coming down, carrying cost is going up more. So if the order quantity is less than Q star, like 1000, you now see the order cost is going up and the carrying cost is coming down. So to the left of it, if you realize, say somewhere here if we are, then you realize that the order cost part is higher, the carrying cost part is lower, but the total cost will always be higher because this is the minimum. So one of the important lessons from the economic order quantity formula is the realization that it is very flat at the minimum, and therefore one need not worry about the decimal or the fraction coming in here. One can conveniently round it off to the nearest 100 and still not incur a significantly high cost. Next thing that we need to look at is, if we are ordering 1224.74 units every time we place an order, now in 1 year we will be ordering 10,000 divided by 1224.74, number of orders n, is equal to 10,000 divided by 1224.74. This 10,000 is the annual demand which is shown here. So I have a demand of 10,000. Every time I place an order, I order for 1224.74. Therefore I have 10,000 divided by 1224.74, that many orders per year. Now this on simplification would give us something like an 8.17 orders per year. Now this raises another question, whether the number of orders per year, should it be an integer or should it not be an integer. The easier thing to do is to assume that let it be an integer. So I order 8 times in a year. So roughly I say I order every 1.5 months. So 1.5 into 8 is 12. So I order roughly every 1.5 months. And it is also convenient that if we make this as 8 orders per year, the order quantity would become 10,000 divided by 8, which is 1250 instead of 1224.74. 1250 is a much more convenient number, and we have already seen here that whether it is 1200 or 1300, we are still in the border of 4900 to 4907, which is hardly 10 rupees on 4800 or 5 rupees. So it is always possible to try and have an integer number here more for the sake of convenience. And when we have an integer number here, and if this is a very comfortable number like 10,000, then the order quantity also becomes a very comfortable number. Or even if it does not become a comfortable number, or it is a fraction, it can always be rounded off to the nearest 100 on either side, and so on. As such, there is no sanctity about the fact that this has to be an integer, need not be an integer. It simply means that if it is 8.17 orders per year, and if the year comprises of 365 days, then it is like 47 days I place an order. So every 47 days or every 46 days I place an order. A plus minus 1 day does not matter at all. The order quantity can be adjusted suitably. But what we learn from this is that even though the actual results of the economic order quantity like 1224, 4898, sometimes or many times they may not be implementable exactly as they are. But the important learning is that we need to fix our order quantities as close to the economic order quantity as possible, subject to other constraints and considerations, so that the cost, actual cost that we incur is still around this 4898.98. Could be this, it could be this, sometimes it could be this, sometimes it could even be this, but it should not be this. So if right now we are having a vendor who is giving us only 4,000, because of which we are incurring an 8,750, if we do the economic order quantity and understand that it is somewhere near 5,000, the next thing we need to do is to see whether our vendor can give this 1,000, so that we get a cost of 5,000. Otherwise we should try another vendor who can give 1,000 and spend an additional 5,000 per year on this item, rather than buy 4,000 at a time and spend 8,750 on that. This is the most important learning from the economic order quantity formula. Now let us move to the next model. The second model is very similar to the first model, except for relaxing one assumption. In the earlier model or the first model, we did not allow shortages or back ordering. Now we are trying to see, at least to begin with mathematically, what happens when we allow the back ordering. We defined 4 costs, we used only 3 of them. We also showed that amongst the 3, one of them does not affect the decision. The actual cost of the item does not affect the decision. We left out the back order stroke shortage cost because of the assumption that there is no back order. Now let us try and allow some back ordering at an additional cost and see how this model behaves. So what we do now is, let us assume that we start somewhere here. So we consume, we reach the point where the stock position is 0. We also assume instantaneous replenishment, which means if I place an order here, I am going to get it immediately, which is what we did in the earlier model. Now we are going to allow a little bit of back ordering. So we do not place an order here, we allow back ordering, we build up some back orders, then we place an order for Q, for an order quantity Q, which is instantly replenished. So it is replenished, and let us say after the replenishment it reaches this point, the point where we started. So once again we consume at the rate of D, like what we did. Once again build some back order, and at this point you place the order for Q and get it replenished instantly, and then it proceeds. So now this is time, this is quantity, now we are going to use some additional notation. Now this part, the quantity that we order here, this is Q. So Q starts from here, this is what we order. So this is our Q, the order quantity. Now this part, which is the back order part, is called small s, which is the back order, and the level to which the inventory gets built up is called IM, maximum inventory, which is here. So obviously Q is equal to IM plus S. Let us say if this is a cycle which we call as capital T, and the cycle repeats. Now this cycle now has 2 parts. This part is called T1, where there is inventory, and there is this part called T2 where there is back order, and T1 plus T2 is equal to T. So now there are 4 costs that we will have. So let the economic order quantity be Q, or the quantity that we order is Q. So the order cost component, so the total cost has TC has all the 4 costs: order cost plus carrying cost plus shortage cost plus item cost. Now Q is the variable which is the order quantity, IM is a variable, S is a variable, but they are related, Q equal to IM plus S. Now if we are going to compute this total cost for a year, then the item cost is going to be D into C. So the item cost will not contain any of the variables Q, IM or S. So like we did in the earlier model, we leave out the item cost. So we are going to have 3 costs in this model. We had 2 costs in the earlier model. So if D is the annual demand and Q is the quantity that we order, the number of orders per year will be D by Q, like we did in the previous model. The order cost or cost per order is C naught. So D by Q into C naught is our total order cost per year. Now we need to look at the total carrying cost per year. The broad or general definition is average inventory into the inventory carrying cost. Earlier it was Q by 2 into CC. Now we have to compute the value of the average inventory. Now if we take any cycle, say a cycle like this, the total inventory that we hold in that cycle is area under this curve, which is half into IM into T1. So this much inventory is held for a period T1 in the cycle, and this is the backorder part of the cycle, so there is no inventory held. So 0 inventory is held for a period T2. The average inventory of IM by 2, just as we got Q by 2 in the earlier, the average inventory of IM by 2 is held for a period T1. An average inventory of 0 is held for a period T2. Therefore, the average inventory as such at any point will be IM by 2 into T1 by T1 plus T2. Let me repeat again. Total inventory held in a cycle is area of this triangle, half into IM into T1. So that much total inventory is held for a total period of T1 and 0 is held for a period of T2. So average inventory is IM by 2 into T1 plus 0 into T2 by T1 plus T2, which simplifies to IM by 2 into T1 by T1 plus T2. This is the average inventory. This into the inventory holding cost, which is CC. Similar manner, the average shortage or back order is 0 for a period T1, average back order of S by 2 for a period T2. So 0 into T1 plus S by 2 into T2 divided by T1 plus T2, which on simplification would give S into T2 by T1 plus T2 into the back order cost, which is defined as CS. So let us now define CS, which is the back order cost. And this is right now defined in the same units as CC. So this will be rupees per unit per year. CS and CC will have the same units, rupees per unit per year. Note the difference. In the earlier model, this was Q by 2 into CC. Now it is Im into T1 by 2 into divided by T1 plus T2 and so on. Basic motivation is that if you take a cycle, part of the cycle which is T1 is the time where we hold inventory, and the remaining part of the cycle which is T2 is where the back order is there. So the inventory portion will contain the area under the inventory curve Im by 2 into T1 for a period T1 plus T2, S by 2 into T2 for a period T1 plus T2. So now this expression for Tc has several variables now. It has Q which is unknown, it has Im which is unknown, it has T1 that is unknown, T2 that is unknown and S that is unknown. But the unknown variables have some relationships. We already saw that Im plus S is equal to Q and T1 plus T2 is equal to some T that we have not used. So we try and simplify this a little bit using some similar triangle property. Now T1 by T1 plus T2 from similar triangles is equal to Im by Im plus S. T1 by T1 plus T2 will be Im divided by Im plus S, but Im plus S is Q. So this will become d by Q C naught plus Im by 2 into T1 by T1 plus T2 is Im by Im plus S, which is Im by Q. So this will become Im square by 2Q into Cc. Similarly, T2 by T1 plus T2 is equal to S by S plus Im, which will give T2 by T1 plus T2 is equal to S by Q. So on simplification this will give S square by, oh I am sorry, there is a 2 that I have missed here, S by 2. So S square by 2Q into Cs. Let me explain it again. When we calculated this portion, which is the back order cost portion, average back order in a cycle is, for T1 part of the cycle there is no back order. For this part of the cycle the total back order is area under the curve half into S into T2. So the average back order at any point in time is half into S into T2 divided by T1 plus T2. So half into S into T2 divided by T1 plus T2. This multiplied by the back order cost is Cs. So on simplification, T2 by T1 plus T2, T2 by T1 plus T2 is equal to S by Im plus S, which is S by Q. So this portion becomes S by Q. So this becomes S square by 2Q into Cs. So now we have eliminated the T1 and T2 from this, because they are also dependent on, they are related to Im and S. So we have eliminated these. Now we have only 3 unknowns which are Q, Im and S, and we also know that they are related because Q is equal to Im plus S. So what we do now is we eliminate Im by substituting Im is equal to Q minus S to get d by Q into C naught plus Q minus S the whole square by 2Q into Cc plus S square by 2Q into Cs. So this way we have now eliminated Im also by substituting Im is equal to Q minus S. So we have only 2 unknowns which are Q and S. The 2 unknowns are how much to order, which is the order quantity, and what is the level of back order, which is the back order level. So Q and S are the 2 unknowns, and now this expression does not have any dependency. All the dependencies have been taken care of by substitution using similar triangles as well as using Q is equal to Im plus S. So now we can differentiate this partially with respect to the 2 variables Q and S to try and get the optimal values of Q and S. So, let us do that. So, first let us differentiate this with respect to q and then we differentiate this with respect to s. So, dou Tc by dou q equal to 0 gives partially differentiating total cost with respect to q would give us. This would give us the term minus d by q square into C naught, which is the same term that we got in the earlier model. So, minus d by q square into C naught plus. Now, this is a term where q appears in the numerator as well as in the denominator. So, here we need to use the u by v differentiation. So, v square will come in the denominator, v du minus u dv by v square. So, we take this Cc by 2 outside. So, plus Cc by 2, u by v will give us v du minus u dv by v square. So, we put a q square here. V du, so this is q into differentiation of this. So, q into 2 times q minus s is what we get, 2 times q minus s into 1. We differentiate this q, you get 1. So, v du minus u dv, q minus s the whole square into differentiation of this q which is 1. So, minus q minus s the whole square is what we have here, this term. This term q appears only in the denominator, so it is easy to differentiate, minus s by 2 q square into Cs equal to 0. This q will give minus 1 by q square. So, minus 2 q square s square Cs be equal to 0, partially differentiating. So, s square will remain as s square Cs is 0. Now, partially differentiating with respect to s, dou Tc by dou s equal to 0 would give us. This term will not contribute anything because there is no s term here. So, this is a constant as far as the partial derivative is concerned. So, this term will not contribute anything. This term has s only in the numerator. So, this will become 2 times q minus s into minus 1 divided by 2 q square Cc plus 2 s square by 2 q, sorry, s square on differentiation would give us 2s. So, 2s by 2q into Cs is equal to 0. Let me repeat, s appears in the numerator. So, 2 times q minus s into minus 1 divided by 2q into Cc divided by 2q into Cc, 2s by 2q into Cs equal to 0. So, this 2 and this 2 will get cancelled, this 2 and this 2 will get cancelled. When you take this q to the other side it goes. So, we have minus q plus s into Cc plus SCS equal to 0, or let me simplify it differently. I will simply take this term to the other side. So, q minus s into Cc is equal to SCS So, QCC is equal to S into CC plus CS, from which S is equal to QCC by CC plus CS. So, this is the first thing that we derive. We have this. Now, we go back to this one, and then we have to use S is equal to QCC by CC plus CS onto this one to try and get the value for Q. We will do that now. Now, I multiply this by 2, so that the 2Q square gets cancelled. So, I will have minus 2D C naught plus CC into, this is 2Q square minus 2QS, 2Q square minus 2QS minus Q square minus S square plus 2QS minus S square CS equal to 0. I have just multiplied this by 2, so that I have this expression. Now, here I can cancel this plus 2QS and minus 2QS, plus 2Q square minus Q square will give me Q square. So, minus 2D C naught plus CC into Q square minus S square minus S square CS equal to 0. Now, this will become minus 2D C naught plus Q square CC minus S square into CC plus CS equal to 0. Now, we substitute for S square from here, minus 2D C naught plus Q square C C minus S square is Q square C C square divided by C C plus C S the whole square into C C plus C S equal to 0. Now, this will go and this will remain. Now, this will simplify to minus 2D C naught. Now, take this here, only here, plus Q square C C into C C plus C S minus Q square C C square by C C plus C S is equal to 0. I am leaving this as it is, I am taking this only up to this. Now, minus 2D C naught plus Q square C C square plus Q square C C C S minus Q square C C square divided by C C plus C S equal to 0. Now, these two terms will get cancelled. So, minus 2D C naught plus Q square C C C S by C C plus C S equal to 0, from which Q square C C C S by or q square CCCS is equal to 2D C naught into CC plus CS, from which q is equal to root over 2D C naught into CC plus CS divided by CC into CS. So, when we use this model where back order is allowed and then we derive, we get the expression S, the back order quantity is QCC by CC plus CS. The order quantity Q is 2D C naught by CCCS into CC plus CS. Now, we can substitute this S and Q back into the total cost function, which is here, to try and find out what is the total cost at the optimum. That and comparison of the model with back ordering, comparing a model with back ordering to a model without back ordering, which means the similarities and differences between models 1 and 2, we will see in the next lecture.